Now we will discuss the solutions for AP Physics, Electricity and Magnetism multiple choice questions year 2009. The first question is: a positive point charge is initially at rest close to a bar magnet that is also at rest. The charge will be attracted to the North Pole, repelled by the North Pole, attracted to the South Pole, repelled by the South Pole, experience no magnetic force. So, we know that both the magnet and the charge are at rest. So, when a magnet and charge are at rest, they do not experience any magnetic force, because only a moving charge is affected by a magnet, and a moving magnet affects a charge which is at rest. So, in this case, both are at rest. So, for the force to exist between a magnet and a charge, one of them should be in moving. So, as both of them are at rest, the charge experiences no magnetic force. So, the answer is E. Resistors of resistance 4 omega, 2 omega, 2 that is ohms, 3 ohms are connected in a circuit as shown above. The currents through the resistors are I4, I2, I3 respectively. Which of these currents is the least and which is greatest? So we have to find which one of them is the least current and which is the the greatest current. So here we see the current that flows through resistor 3 ohms also flows through both 4 ohms and 2 ohms. So the greatest current must be flowing through I3. I3 is the greatest current, because the same current is flowing through here, two resistances. So I3 should be the greatest current. Now in this case, the resistance 2 ohms and 4 ohms, the more current flows through 2 ohms, because the current tries to take the path of least resistance. So there will be more current through 2 ohms than 4 ohms. So the least current flows through 4 ohms. So the answer is the least is I4 and the greatest is I3. So the answer is A. Which of the following is a possible unit for electric field? So electric field is force per unit charge. So the unit of force is Newton, the unit of charge is Coulomb. So Newton per Coulomb is the unit of electric field. An EMF is induced by a changing magnetic flux in the operation of all of the following except. So electric generator, the electricity is generated by changing magnetic flux. So there is a coil and which rotates inside a magnet. That is how electric generator works. So there is a change in the magnetic flux in electric generator. Transformer, it is a changing magnetic flux which transforms the voltage. Eddy current brake works on the principle of changing flux. Inductor, also there is a changing flux. When alternating current flows, there is a changing flux. So the only instrument in which the changing magnetic flux does not happen in its operation is a mass spectrometer. So the answer is E. A solid conducting sphere carries a charge plus Q. Which of the following is true of the electric field E and the electric potential V inside the sphere? So the conductor is an equipotential region. So once it is equipotential, then the electric field, the force required to move a charge in an equipotential is 0. So there is no field. So the answer is B, that the field is 0, but V is not equal to 0, and it would be constant in a conducting sphere. A capacitor with circular parallel plates of radius R that are separated by distance D has a capacitance of C. What would be the capacitance if the plates had radius 2R and were separated by distance D by 2? So the capacitance is proportional to the area and inversely proportional to the distance. So once the radius is increased by 2R, the area increases by 4, that is pi r square. So the area increases by 4, and the distance when it is decreased by 2, the ratio of the area to distance will be multiplied by 2, so the area by 4, and because of d by 2 there is a multiplication of 2, so the capacitance increases by 8, so the answer is 8C, so that is E. A network of 3 resistors is connected to a 20 volt battery. What is the equivalent resistance of the network? So when the resistances are connected in parallel, then here we can see the series resistance. This is 8 kilo ohms. They are in series, so they can be added. Now the 8 kilo ohms and 8 kilo ohms, when they are in parallel, so it becomes only half. So 4 kilo ohms is the effective resistance of the network. So the answer is A. What is the potential difference between the points X and Y? So the potential difference between, because the resistance 8 and these are in parallel, so between this point and this point the potential difference is 20, and the resistances are of equal value, so the potential drop should be equal on this resistance and on this resistance. So 20 by 2 is 10. 10 volts is the potential drop between X and Y. So the 7th question answer is A, and the 8th question the answer is C. 10 volts. Okay. The single circular wire loop of radius R shown above carries a current I that produces a magnetic field B at the center of the loop. If the current remains constant while the loop is enlarged to a radius of 2R, what happens to the magnetic field at the center? So we know that the magnetic field is the magnetic field B of a circular loop magnetic field of a circular loop magnetic field is given by mu 0, which is magnetic permeability, I by R. So once the radius is doubled, so B becomes B by, this is doubled, R becomes 2R, then this becomes B will be, suppose if this is B0, so this will be B0 by 2. So the answer is that it decreases to B by 2. Now, a capacitor charged to a potential difference V stores an amount of energy U0. If the potential difference is doubled, what is the new stored energy? See, the new stored energy, the energy in a capacitor is given by U is equal to 1 over 2 QV. So Q actually, again, because it depends on the potential, so we need to write this in terms of potential. So Q is V. So already there is a V, so this becomes V square. So once the potential difference is doubled, so if this is doubled, so this goes by 4 times. So the answer is E. (11 and 12). a uniform magnetic field B directed downward parallel to the plane of the page exists in the shaded region. That is this side, and here it is not there. So an electron can enter the field from different directions. It can enter like this, in all directions. Suppose that the electron is moving straight down in the same direction as B. It moves like this. When it enters the region of the magnetic field, what is the direction of the magnetic force, if any, on the electron when it first enters the field region? When it enters the field region, both are in the downward direction, and because the magnetic force acts on a charge only when the motion of the charge is having some component of velocity perpendicular to the field. So in this case it is parallel, so the magnetic force is 0. So the electron does not experience any force when the velocity is parallel to the direction of the magnetic field. So the answer is E, none. There is no magnetic force on the electron. Now, if the electron is moving perpendicular into the plane of the page where it enters the region of the magnetic field, what is the direction of the magnetic force, if any, on the electron when it first enters the field region? So here the magnetic field is acting downwards, and the electron's direction is into the plane of the page, so which is perpendicular. So we can apply the right hand rule, and then the force exerted on the electron will be to the right. Basically, for the conventional current, it is to the left, but this is electron negative charge, so the direction of the force on the electron is to the right. Yeah, here the magnetic field in the minus z direction downwards, and the velocity of the electron is going in this direction, that is minus x. Here we have written the xyz coordinate system. So the electron is entering into the plane of the page, that is minus x. The magnetic field is down, that is minus z. So the force is V cross B, so that is minus x into minus z. This gives us minus y, because xz is minus y. That is for the positive charge. Now because the charge is negative, so this becomes plus, so the force on the electron would be to the right. So the answer is to the right. If it is proton, it will be to the left. The following are configurations of electric charges located at the vertices of an equilateral triangle. Point P is in the plane of the triangle and equidistant from the charges. So now what we have to find out is in which configuration is the electric field at P pointed directly toward one of the charges. So here we can see, in this case all are in the first case the charges are all positive. So this, if this is positive, so this will be repelling, and these two also will be repelling. This charge will be, Q will be repelling this side, this will be repelling it this side, and this will be repelling the other side. So here the forces will be actually here the forces will cancel. The electric field in this situation is 0, because we can resolve this and this force into components along horizontal and vertical. The horizontal components will cancel, and the vertical components of the two charges cancels with the vertical component of this charge. So this is a situation where the electric field is 0. So in this case, these two charges will repel, and whereas so the resultant of this will be in this direction, and this attracts it, so the net force will be towards minus Q. So the electric field, which is the direction of the positive charge, he is here towards this charge. So the answer is B. In which configuration is electric potential at P equal to 0? So the configuration in which the sum of the charges is 0, because the potential is given by the charge by the distance. So distances are the same. So the numerator you have the charge, denominator you have the distance. Distances are common, same. So if the numerators add up to 0, then in that configuration the potential is 0. So we can see here minus 2q minus 2 is minus 3q plus 3q, this is 0. So the answer is E. So in this configuration the potential is 0. The electrical potential is 50 at point X and 70 at Y. What is the minimum average power needed by external force to move a charge of 4 microcoulombs from rest at X to rest at Y? So that is only the energy difference between 70 volts and 50 volts. So 70 volts is a higher this thing. So for a charge to be, a positive charge to be moved to 70 volts, so we have to apply energy is equal to the 20 volts is the energy required for unit charge to move from 50 volts to 70 volts. So here the charge is 4 microcoulombs. So we need to apply a energy of 20 volts into 4 microcoulombs. That is the energy that's to be applied for the charge to move to 70 volts. So 80 microcoulomb volt by, that is joules, by, because volt is joules per coulomb. So we will have 4 microcoulomb into 20 volts by 5 seconds. That is the time in which the energy has to be delivered. So that gives us the average power. So which is 80 by 5 is see, this is 1.6 into 10 to the power of minus 5 watts. That is the answer is E. The problem 16, a small circular loop of conducting wire is near a long straight wire that carries a steady electric current I to the right, as shown above. Which of the following actions will result in a clockwise induced electric current in the wire loop? So the induced current opposes the change in magnetic flux. That means the clockwise current here will induce magnetic field into the plane of the loop. So if there is the magnetic field, changing magnetic field because of the change in the current of the wire increases the magnetic field coming out of the plane of the loop, then that will induce current in the loop to oppose the increasing magnetic field. So if the magnetic field is coming out of the field, that is increasing, then the current, clockwise current, will produce magnetic field in the opposite direction to cancel the increasing magnetic flux. So the magnetic flux coming out of the plane will increase if the current in the wire increases. We can apply the right hand rule. If the thumb is pointing in the direction of the current, the fingers, the curled fingers, will point in the direction of the field. So if the current increases in this direction, the field will increase in the direction coming out of the plane of the loop. So that will create current in the clockwise direction in the circular loop. So yeah, the current in the straight wire is steadily increasing. So that is the answer. So answer is 2 only. That is B. Two long straight horizontal wires parallel to each other in the plane of the page carry electric currents to the right as shown in figure above. What is the direction of the net magnetic field at point P midway between the two wires. Now here the current which is flowing in this direction creates a field which is out of the plane, whereas this creates into the plane. The 20 amperes creates into the plane. We can again apply the right hand rule. The thumb pointing in the direction of the current. If you curl the fingers, and the fingers will show you the direction of the magnetic field. So this will give magnetic field into the plane of the page. This gives out of the plane of the page at this point. So this is more 20 amperes will create a larger magnetic field. So the net magnetic field will have a direction into the plane of the page. So the answer is D. Two circular loops of wire P and Q are arranged coaxially. The current in P is in the direction of the arrowhead. So there is a current flowing in P in this circular loop in this direction. This is the current. Which of the following is a correct statement? If P is moving toward Q, the current is induced in Q in the direction of the arrowhead. Now if P is moving towards Q, now this will create magnetic field. Applying again right hand rule will create magnetic field in this direction. So this will in this direction, the current here, if this is the direction of the current, this is clockwise. So clockwise current in the loop creates the magnetic field into the plane. So when P moves towards Q, the magnetic flux in this direction will increase. So then to oppose the increasing magnetic flux into the loop, the current has to flow in the anti-clockwise direction to create a magnetic field in the opposite direction. So it will not be in the direction of the arrowhead. So A is not the answer. B. If Q is moving toward P, a current is induced in Q in the direction opposite to the arrowhead. So when Q moves towards P, again it is only the magnetic flux that will increase. So the magnetic flux into this plane will increase. So to cancel that, the current has to move in the direction opposite to this arrowhead. So B is the answer. In the circuit shown above, the capacitor is initially uncharged. The switch S is then closed. Immediately after the switch is closed, the current in the 3 omega resistor is most clearly. So immediately after the switch is closed, the current flows in the entire circuit. Because this is not charged, the current will flow like this, will flow like this. So effectively, these resistances 6 ohms, 6 ohms, 3 ohms, all of them will be in the circuit. So the total resistance, this plus this, is 3 ohms, because these two are parallel. The effective resistance is 3 ohms. So this is 6 ohms. So 6 volts and resistance of 6 ohms. 6 volts is a potential difference. So the current will be 1 ampere. So the answer is A. But when the switch is closed after a long time, then the capacitor will be charged. Then there is no longer current flows here. Once this is charged, the potential is raised here. So then there is no, the current doesn't flow. The potential here and the potential here will be same as the potential. So there is no current in the In this branch, there is no current. The current flows only in the through 6 ohms and 3 ohms. So a long term after the switch is closed, the current in the 3 ohms resistor is most nearly, so we have to take into only 6 and 3 ohms, so 9 ohms, 6 by 9, so that gives us 0.67 amperes. So the answer is D. After a long time the switch is closed, see the potential difference across the capacitor will be same as the potential difference across this resistance, and the potential difference is this point and this point will be 0. There is no current here. So the current flows only through this, and capacitor there is no flow of current. But the potential difference across the capacitor plates is same as the potential difference across the 6 ohms resistance. Yeah, this is an interesting problem. A negatively charged particle initially in region 1, as shown above, is accelerated from rest by an electric field of magnitude E0 between two parallel plates separated by a distance d. The particle then enters region 2, the space between two parallel plates with separation 2d and an electric field of magnitude 3E0 in the opposite direction. How far into region 2 does the particle travel before reversing direction? So basically this we can look at as from the point of view of conservation of energy. We could also calculate in terms of velocities and acceleration. So we can find out when the velocity, by the time it comes here, it picks up velocity, and then the opposite force, then the velocity becomes 0, then it will reverse. So that is one way, but that will be more tedious. So the simpler way of doing this is apply the conservation. This is like electron, it comes here, it is like it falls into a potential well, and then because of the velocity it tries to go against the, it climbs. So obviously it will climb until it loses all its energy, it becomes potential energy. So here the energy that is gained by the electron is E0 into D. E0 is a force and D is the distance, a force into D into the charge, okay, electron charge we can take. So that is the energy that it gains. The electron, the E0 D is the energy gained per by 1 coulomb of charge. So if we can multiply the charge of electron to get the energy gained by the electron. So now this it will move here until the kinetic energy that it has acquired gets converted into potential energy. So it has to move. The force into distance here should become E0D. So the force here is 3E0. Now for it to become E0D, it has to move a distance of D by 3. 3E0 into D by 3 is E0D. So it will move till a distance of D by 3 before it reverses the direction. So answer is A. A student wants to construct an inductor of a given inductance using copper wire and a plastic tube. If a sufficient supply of copper wire is available, the student will also need. So we know the inductance is related to the number of turns and number of turns per unit length. So here, for us to find out number of turns per unit length, we need a meter stick. So the answer is A. Correct statements about a constant magnetic field acting on a charged particle include which of the following? So if the field is constant, a magnetic field, it acts on the charge. So then we know that the force that is acting is V cross B. So the field can accelerate the particle. Of course, it should not be in the direction of the motion of the particle, then the field can accelerate the particle. The field can change the kinetic energy of the particle. No, it cannot change. It is a B cross B. So the force is always perpendicular to the movement. Velocity is so like a circular motion. So there is no change in the. It doesn't do any work. A magnetic force doesn't do any work on a charged particle. So both 2 and 3 are not correct. So only correct is 1. The field can accelerate the particle. So the answer is 1 only A. A metal wire has a resistance R when it is at a temperature T. The wire is melted and all of the metal is used to reform it into a new wire 4 times as long. What is the resistance of the new wire at a temperature T? So now what is done is it is melted and made lengthier. So, but the material in the wire is conserved. So that means the volume of the wire has not changed. The length has changed. So the area also changes. So we have to find out what is the new resistance. Now the resistance is given by the resistivity, which depends on the material, the length by the area. So volume is constant, so we can replace this by area is nothing but V by L. This gives us rho L square by V. If length is made 4 times, so it becomes 16 rho L by V. So the 16 rho L square, 16 rho L square by V. So here this was rho L square by V. That's what we are having here. So it becomes 16 times. So the answer is 16 times resistance. So the answer is E. So here the point is that we have not worked with the area, that is, then the calculation becomes more long. So simply replace A with value, then we know the resistance becomes only a function of the length, because the volume is conserved. So the answer is 16R. So the answer is E. An isolated hollow conducting sphere carries a total positive charge Q. Correct statements about the electric field produced by the charged sphere include which of the following? It is directed radially outward from the surface of the sphere. That is, for any conductor, the electric field will be perpendicular to the surface, because the conductor is an equipotential area. So the field is perpendicular. So the charges can move freely on the surface. So it is. So the radius is perpendicular to the surface in case of a sphere. So 1 is correct. It is equal to 0 outside the sphere. No, it is not equal to 0 outside the sphere, because the field outside depends upon the charge enclosed. So we can apply the Gauss law. So it is the field into the E dot ds is equal to Q. So it doesn't. It is not 0 outside the sphere. It is equal to 0 inside the sphere. And that is true. This is The sphere, conducting sphere will have equipotential inside. So the field is 0 inside the sphere. So the answer is 1 and 3. So answer is D. It's 25. The diagram above shows the electric field lines due to two charged parallel metal plates X, Y. No, two parallel metal plates, and X, Y, Z are locations where charges may be placed. Charges may be placed X, Y, and Z. Which of the following is true? Now, the left plate is positive and the right plate is negative. The left plate is positive, no. That is because the field lines are in towards the left, so they go from positive to negative. So the left is not negative. So this left is not positive. So this only is positive. Okay, and negative charge at X experiences a greater force than if it were placed at Y. A negative charge at X experiences a greater force than if it were placed at Y. No, because both are at the same distance from the plate, so they cannot they cannot experience a greater force. A positive charge at X experiences less force than if it were placed. No, that is also not true. Both will have the same this thing. A negative charge at X experiences less force than it were a negative charge at X experiences less force than if it were placed at Z. No, actually, the field inside the plates is the same everywhere, so it doesn't experience less force. The field is uniform between the capacitor plates, between the plates of a capacitor. So, a positive charge at X would experience the same force if it were placed at Z. So, this is true because the field is uniform. Actually, the way the lines are drawn, it indicates that the field is uniform. So everywhere the field is the same, so they will experience the same force. So the answer is C. When two metal objects X and Y are connected to each other by a conducting wire, object X gains electrons. From this information, it can be inferred that before the connection was made, object X compared with object Y must have had greater electric potential. Why? Because great electric potential means that it has got a positive charge. So that's how it gains electrons, because it has a positive charge. So electrons will move towards it. So it has a greater electric potential. That is, we have there are two objects. Now this is X and we have Y. Now we conduct a wire. If there are neutral, then no flow of electrons. Now what happened? X gained electrons. This has gained electrons. So for this to gain electrons, so this must have excess electrons. Then only this will gain electrons. So that means this is at a higher potential. This relative to this has got positive charge. So this is at a higher potential. So that's how the electrons move to X. Two long straight current carrying wires are parallel to each other in the plane of the page and separated by a distance A, as shown above. The direction of the current in each wire is toward the top of the page. Which of the following best represents the force per unit length acting on the wires? So now here the current is like this. So this will create a magnetic field out of the page here, and this will create a magnetic field into the page. So the magnetic fields are in opposite directions. So then because they are opposite polarity, so there will be an attractive force of magnitude mu0 I square by 2 pi a. So answer is C. Here the magnetic field due to a wire is given by mu0 I by 2 pi a, and the force is given by F is equal to I LB. Now we are talking about unit length, so this goes. So that is how we get force is mu0 I square by 2 pi a. Here is the spacing between the two wires. So that is how it is an attractive force of magnitude mu0 I square by 2 pi a. See, a negatively charged rod is brought near a metal object on an insulating stand as shown above. When charges stop moving, the left side of the object has an excess of positive charge and the right side of the object, where the radius of curvature is less, has an excess of negative charge. Which of the following best describe the electric potential on the metal object? First, the electric potential on a conducting thing will be uniform everywhere. So that is the this thing. So because this is a metal, the potential has to be same everywhere. Otherwise, it will lead to movement of the movement. If the potential is not uniform, there are free electrons, so they will move. So it results in a potential which is same everywhere. So the answer is D. Problem number 30. Four identical charged particles, each with charge Q, are fixed in place in the shape of an equilateral pyramid with sides of length L as shown above. What is the electrical potential energy of this arrangement of charges? Here the potential energy of charges to calculate we have to take in pairs. Now with this, the potential energy will be Q square by L. So like that we will have 1, 2, 3. So there are 3 pairs. So then with this we will have 2 pairs. So 3 plus 2, 5. Then with this we will have between the two 1 pair. So there will be 6 Q square by L by 4 pi E0. So that is the potential energy of the configuration. So the answer is C. So here, one of the fourth charged particles is released and allowed to move away under the influence of electrostatic force from the other three charges. How much kinetic energy will it have when it is very, very far away? So, see, potential energy of the kinetic energy of the charge when it goes far away will be the potential energy of the original configuration minus the potential energy of the new configuration. So the new configuration, one charge goes away, then we'll have one charge with this, there are two pairs, then with this and this three pairs. So 3q square by L, whereas the original configuration potential energy is 6q square. So the difference is 3q square by L. So the answer is C. That is basically we have applied the conservation of energy. So of the configuration. See, the original configuration, the total energy is potential. In the new configuration, it is a part potential and part kinetic energy. So conservation of energy gives us this answer, which is C. So here we are given the resistance of the wire, then we are given the area. So the potential, if there is a potential which is developed in the wire, so then the resistance, potential, and current are related by this equation. So the current is equal to V by R. Now, what is the potential induced EMF is created by changing magnetic flux, which is dV by dt into the area. Then this R is here. So then we can find out what is the change in magnetic field is IR by A. So we can substitute for I 1 milliampere, and then R is 30 ohms, and then A is 3 square meters. Then this gives us 1 into 10 to the power of minus 2 Tesla per second. So the answer is D. The capacitors are connected like this, and this is X capacitor and this is Y. They are connected in series across a battery. A dielectric is placed here, and because they are connected in series, whatever charge is here must be here. So similarly, so that means the charge on this capacitor and this capacitor would be same. Actually, the charge here will be in the opposite opposite charges. If this is plus here, this is minus. So here this is plus, then this is minus. So opposite charges. So the charges will be the same. So, but because the capacitance of the dielectric will be more, so Cx is greater than Cy. Q is equal to Cv. So when Cx is greater than Cy, then Vx will be less than Vy. So we can see Qx is equal to Qy, then Vx is less than Vy. D is the answer. A small sphere of mass m and charge plus q is constrained to move vertically in an insulating cylinder as shown above. At the bottom of the cylinder is a point charge plus q. At what height h above the bottom of the cylinder will the small sphere of the mass m be in equilibrium. So this equilibrium condition is this positive charge. It will repel this, whereas the gravity, the force of gravity, it attracts it downwards. So, or the potential energy and the gravitational energy, when they are equal, This gravitational energy is negative and the potential energy is positive. So when it is repelling, whereas that is attracting. When they balance, then the small charge will be in equilibrium. So we have QQ by H 4 pi some constant is equal to mgh. So by uh, manipulating this, we will get the height is nothing but under root QQ by mg, and 4 pi is 0. So this is some constant. So the answer is E. Answer is E. The magnetic field acting on this segment doesn't give any force because they are parallel. The current flowing through this is parallel, whereas the current here is perpendicular to the magnetic field, so that gives a force. So which is nothing but the force is B into D. Then the torque is, there is a this is the distance between the see here the force is in one direction, here the force is in the opposite direction. So the distance between is a D, so into D, so the force will be, the torque will be proportional to D square. So the answer is B, directly proportional to D square.